Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another video in a series on optimization problems for calculus. And you should have already watched my video on tactics for setting up and solving optimization problems in calculus. And at this point, we're just going to start talking about areas. I already did a video on minimizing distances. Now we're going to maximize areas. The first problem is more of a theory problem just to get us started. So find the maximum area of a rectangle inscribed in between the x-axis and the function negative x to the fourth plus 3. The key word here is inscribed. If you don't know what that means, it just means you have a rectangle that is inserted into the interior of this region between the x-axis and that function. So we've read the problem, and if you still don't understand because, well, that word inscribed is kind of a hefty word here, we're going to go ahead and draw it so that I can create some level of understanding here. Let's bring in a ruler and we'll just draw out an x-axis because that's what we want to have to inscribe the rectangle between the x-axis and the function. And then I will draw on a y-axis and then I'll draw in the function. The function itself is an upside down parabola-like function. When x is 0, y is 3. So 1, 2, and 3. And this reaches the the x-axis when the, when x to the fourth is 3 or at 3 to the 1/4 power. So it does something like this. It's a little flatter than a parabola because it's got a higher power than the square power. And it strikes the x-axis when x to the fourth is equal to 3, or in other words, at 3 to the 1/4 power here and a negative 3 to the 1/4 power there. And what we're going to be doing is inscribing or inserting a rectangle. So let's go ahead and see how that works. I think honestly a ruler again is going to be very helpful. I'm going to just put in a sample of a rectangle. This is not the optimal rectangle, but it is a sample rectangle. So bump, and let's move this over here. There we go. And this right here that looks like a square, doesn't it? That's unfortunate, but okay. So there is a rectangle. You should notice that I could technically have an infinite number of kinds of rectangles in here. In fact, I could have my rectangle have struck the curve right there and created something like this. Let me get this. I'll try to do this as accurately as possible. So that could be my rectangle. So you just don't know what size that rectangle is, but we want to find the rectangle so that it is maximized. We've maximized the area. So we want this area here to be as large as possible. Obviously, you can make the area super duper small. You could totally minimize the area very easily. If you're wondering how it's easy to minimize the area, well, create your rectangle so that its height it barely has a height to it. So something like this, right? That area right there underneath that rectangle is going to be super small, if not 0. The lower that the y value hits, the less the area is. All right. That being said, so hopefully we understand this. Now we're going to go ahead and label a few things. The point where my rectangle hits the curve, I'll call that point x comma y. And let's see, what do we want to, the step 3 I really don't have to do, but the step 4, this is where I want to state what is being optimized here. Well, we want to find the maximum area of that rectangle. So we need to maximize area. Maximize area. Well, what is the area of a rectangle? It's super simple to answer, right? You've done this since you were in pre-algebra, maybe. Area is equal to length times width, or length times height. And the length or width, whatever you want to call this distance right here is what I will call L, and this distance right here is what I'll call height. Of course, it's easy for you to see that L is 2 of these x values. I hope you can agree with that, because this is x comma 0. This point right here is 0 comma y. So that length is just 2 of those x values. So I'm going to say length is 2x. The height of that rectangle is just the y value. So really we want to maximize or optimize or find the absolute maximum of this equation, or this function, area function right there. But unfortunately we have way too many variables. We have 3 variables. So I need a way to relate out one of those variables. And I wish I had a way of saying there's a relationship between x and y. I mean, here it is sitting on this curve, you know, the curve where y is equal to negative x to the 4th plus 3, but I just have no clue what the relationship between x and y is. Oh yeah, I do. It's negative x to the 4th plus 3, because that's the equation of the roof, I guess you could call it. So now our master equation is area is equal to 2x times a negative x to the 4th plus 3. We want to maximize that function. That area function, by the way, is not it's not any of those curves that are sitting over here. It's not this stuff. So you're not looking at the maximum of this curve. You're looking at a maximum of a completely different function. And just cleaning this up, this is going to be a negative 2x to the 5th plus 6x. And to maximize this, we want to find the critical numbers. And the critical numbers, they occur when your derivative is 0 or it does not exist. Well, in this case, our derivative always exists, but it is equal to a negative 10x to the 4th plus 6. So a prime, our derivative, is equal to 0 when 10x to the 4th is equal to 6, or in other words, x to the 4th is equal to 3/5. Yeah. And that's when x is equal to 3/5 to the 1/4 power. Now again, with earlier material, when you're trying to find an absolute maximum or an absolute minimum, you would check the edge points. And we still might have to do that here. Let's go ahead and start with the fact, though, that our area is at minimum. What's the smallest value for x? Because our area is a function of x. Remember, that x value is from over here. What's the smallest value x could be? Well, 0. 0 is the smallest value x can be, so our domain is going to start at 0. The largest value x can be, just according to our picture here, is going to be this 3 to the 1/4. Those are the edges of our realistic domain in this problem. If you want to evaluate the area at those edges, you're more than welcome to. You'll find out that there's 0 at both edges. And you can also visualize that if you created a rectangle that was inscribed within this region where the x value was 0, you would just have, I can't even draw it in, honestly. You would have a rectangle like this, which has 0 area. So that's important. Also, if you wanted to have a rectangle where its right edge occurred at 3 to the 1/4 power, this would be your rectangle, and it would have 0 area as well. So our critical number is the only candidate we'll have for a maximum. Our critical number occurs again at 3/5 to the 1/4 power. You can grab a calculator and figure out what that number is. I'm going to go ahead and do that since I have a calculator right in front of me. So 0.6 raised to the 0.25 power, that's right, is 0.88 roughly. So I'm just going to put this in here that it's roughly 0.88. It's not exactly, but whatever. You could plug in any number less than 0.88 into the derivative of a. If you do that, I'm going to do a half. Okay. So if you plug in a half, 1/2 to the 4th power is 1/16. And so let's see, -10 times 1/16 is less than 1. Add 6, that's positive. So we have positive. So our function will be increasing. And then plug any number in that's greater than 3/5 to the 1/4 power. And 1 is greater than 3/5 to the 1/4 power. So if you plug 1 in, you get -10 plus 6, which is negative. So your function's decreasing. So you did find the local max, and in this case, because it is the only maximum on this curve on the interval, it's the absolute max. So we have found where our curve gets an absolute maximum, and our curve is the area curve. So the area is maximized when x is equal to 3/5 to the 1/4 power. And that area is, and then I can go over to my area formula, which is just this guy right here. And I'll plug into my calculator. Let's see, it's a -2 times that answer to the 5th. Close that. Plus 6 times that answer. And I get the following. I'll just round it to the nearest tenth. 4.2 square units. So the area is roughly 4.2 square units. I don't know what the units of this are, or is what the units are. Anyway, it doesn't really matter. I don't know what the units for this problem are. Anyway, all right. Okay, so this problem is done. Now we'll move on to the second problem. All right, our next problem here, we have a gutter that's supposed to be made of a strip of metal 26.7 inches wide, with the cross section having the form of an isosceles trapezoid. And I say as shown below because there's a little bit more information that you need to be given here. Find the depth of the gutter that gives a maximum cross-sectional area. Well, we've read the problem. Let me just draw out what they mean. So we have a sheet of metal here. This is a sheet of metal. It's 26.7 inches wide. And this is going to be used for, let's say, a rain gutter or something like that. Now, the isosceles trapezoid that they're talking about, it's more than just an isosceles trapezoid. It's going to be a trapezoid where it's not only isosceles, which just basically means that these side lengths are the same, but it's going to be a trapezoid where the bottom length is also the same as those three sides. That's not technically the definition of an isosceles trapezoid, but that's what that's the extra assumption we're going to make. Let me draw this a little more cleanly so that it's not such a mess here. So there's a cleaner picture. And what we're going to do is split up that 26.7 inches into 3 sections. So the bottom section here will be 26.7 inches divided by 3. This side length here will be 26.7 inches divided by 3. And 26.7 inches, 0.7 inches divided by 3. Altogether, obviously, those should sum up to 26.7 inches, which they do. It's isosceles because these two sides are the same length, but it's a special isosceles trapezoid where the base is also the same length. And we want to figure out what is the correct kind of bend to this metal so that we can maximize the water flow through here for this gutter. And that it comes down to just asking what is the best depth here. It's an equivalent question. What is the best depth? And I'll call that depth D. What is D so that we can get the maximal area here? Well, that comes down to actually noticing this is 3 regions. And you can find, these are right triangles off the edge, by the way. You can find the area of each of these regions and add them up. And we're going to maximize the area. So we want to maximize the area. And the area itself is equal to the area of, I'll say area 1 plus area 2 plus area 3. Obviously, area 1 and area 3 are the same. So this is going to just be twice area 1 technically plus area 2. And area 1 is a triangle, and that's just 1/2 base times height, right? So that is going to be a little math problem that we'll have to figure out there. Let's just say it's twice times 1/2 base. The base of this I'll call D, and the height I'll call X. So 1/2 base times height. And then plus the area of that central rectangle, and that will be 26.7 divided by 3 times D. Now you can see in this area formula, we have one too many variables. We have to get rid of that X. Again, I'm looking at this triangle. Triangles have areas of 1/2 base times height. Their hypotenuse doesn't come into play, well, directly at least, into that. So the area of this is 1/2 D times X. But we can find what X is by using the Pythagorean theorem. We happen to know that X is going to be the square root of that 26.7 over 3 being squared minus a D squared. That's what X is equal to. So I'll go ahead and plug that into my area formula. And that's the relating equation, if you will. So this will be D times the square root of 26.7 thirds squared minus D squared. Is that right? Yeah, it is. Yep. And then plus that number, 26.7 thirds D. Now there are little tricks you can do here in mathematics to make your life a little bit easier. So what I am going to do is I'm going to let C equal 26.7 over 3. It's just a little bit easier for me to do my handwriting that way. So A is actually equal to D square root of C squared minus D squared, where C is a constant, plus CD. If you can do this type of manipulation, it really does make your life a little bit easier. Now let's talk about the domain of this function. The domain of this function is important so that we can figure out what is the best, what's the interval we'll have to test when we test for maximums and minimums. In this case, the depth, well, the lowest the depth could be is 0 if you had not unfolded, or if you had not folded those edges. So the depth D, the minimum it's going to be is 0, and really it's never going to actually equal 0 because there's always going to be a slight bend to this gutter. So the domain of this is going to start at 0 and go to, well, if you bent these edges all the way vertical, then D would be this length here, 26.7 over 3. So again, it goes all the way up to 26.7 over 3. And actually probably could include that, I suppose. But not a big deal. And if you want to say it could include 0.2, that's fine. It's not that big of a deal, honestly. The area, well, technically the area would be really weird there, so you can't do that. Anyhow, so let's go ahead and find the critical numbers of this equation. Remember, the critical numbers occur when A prime is 0 or A prime does not exist. Well, A prime is equal to, we have a, you know what I'll do? I'll do it like this. This is D times the square root of C squared minus D squared plus C. That way I don't have to do a product rule and then another derivative. I could just do a product rule. That's good. So the derivative of the first, we're taking, when I say A prime, it's the derivative of A with respect to D. Okay. So the unfortunate use of that letter D, by the way. The derivative of D is 1. So that's the derivative of the first function times the second is root C squared minus D squared plus C. So it's 1 times that plus D times the derivative of this second function, the derivative of all of this right here. And remember, c is a constant, so the derivative of that plus c is 0. All right, so the derivative of the square root is going to be 1 over 2 times that square root times the derivative of the argument, or the radicand, if you will. And remember, c is a constant, so that's 0, but the derivative of a negative d squared is a negative 2d. And then plus, like I said, 0. All right, so let's see what happens here. A prime is equal to, we have the root c squared minus d squared plus c minus d squared over root c squared minus d squared. It would be a good idea maybe to set these, well, no, you're not taking a second derivative. It's fine. You should notice that this does not exist when d is equal to c. So d cannot be equal to c, so our domain actually will not include that edge c. That's fine. But otherwise, we're fine. And so we want to go ahead and set this equal to 0. A prime is 0 when I'll move this fraction to the left-hand side and pretend as though a prime is 0. So that would give us d squared over root c squared minus d squared is equal to root c squared minus d squared plus c. I will multiply both sides by that square root. So that gives me d squared is equal to c squared minus d squared plus c root c squared minus d squared. Remember, c is a constant. I'll add d squared to both sides. And I'll also subtract c squared from both sides. And this is part of your prerequisite kind of skills in solving radical equations. You're just solving for d. Well, you have to square both sides to solve for d here. So squaring both sides, we get 2d squared minus c squared being squared is equal to, square the right-hand side, you get c squared times c squared minus d squared. This is, trust me, a lot easier than using that 26.7 divided by 3. So you can see the algebra is a little bit heavy here. Multiplying out the left-hand side, you get 4 of those d to the fourths minus 4 of those c squared d squareds, and then plus a c to the fourth. And on the right-hand side, you get a c to the fourth, very convenient, minus c squared d squared. The c to the fourths cancel beautifully. I'm going to add c squared d squared to both sides. You get 4d to the fourth minus 3c squared d squared is equal to 0. Factor out a d squared, and you're left with, I don't need that type of bracket, I guess, 4d squared minus 3c squared is equal to 0. The solution to this would be either d equals 0 or 4d squared minus 3c squared is equal to 0. Add 3c squared, divide by 4, and take the square root, and you get d is equal to, technically plus or minus, the square root of 3c over 2. However, d will not be, d is a depth, it will not be negative, so we're just going to deal with the positive. Now, draw a number line. Remember that our domain goes from 0 to c, so we don't really have a lot of room to play with here. Our critical numbers actually occurred when d was 0 and when d is c root 3 over 2. C root 3 over 2 is probably right around here, let's just pretend. And here is where I'm actually going to figure out what c root 3 over 2 is. Remember, c is 26.7. Where did I make that substitution? There, right up there. C is 26.7 divided by 3. So I'm just going to grab a calculator, type in 26.7, and then I'll divide that by 3. I'll save that as an answer. That's 8.9. That's pretty nice. So I'll just say 8.9. 8.9. And now I'll figure out what 8.9 times the square root of 3 being divided by 2 is. And that is roughly 7.7. So we have a critical number at 7.7 for our derivative, which, by the way, is this busyness right here. All right, so if you plug in a number less than 7.7, try 1 for D. So A prime at 1. Well, remember, you're plugging in for D, and C is C is 8.9. 8.9 squared minus 1 squared, that's obviously positive, plus 8.9, that's still positive, okay, minus 1 over that square root. I'm going to say 1 over that square root is very small, so that's positive. And so our function is increasing here. Our area is increasing. Now, if you plug in a number greater than 7.7, that's what C is. Is that right? Yeah, that's what a critical number is 7.7. So plug in a number greater than 7.7. Let's plug in 8. If you were to plug in 8, remember this is 8.9 squared minus 8 squared, that's positive. Okay. And in fact, you might have to grab a calculator for this now that I'm thinking about it, because that is going to be a bit of a mess. So A prime at 8 is the square root of 8.9 squared minus 8 squared plus 8. C is 8.9 plus 8.9 minus 8 squared over the square root of 8.9 squared minus 8 squared. I'm going to quickly compute that. That's negative 3.6, but all that matters to me is it's negative. So I know that my area is decreasing at that moment. So my area went from increasing to decreasing. That is a local max, and it's also on that interval, the absolute maximum. So we have found out what the depth is to maximize our area of water flow there. And the real question really was find the depth of the gutter that gives a maximum cross-sectional area. They didn't ask for the maximum cross-sectional area itself, so I'm not going to respond to that. I'm just going to say depth should be 7.7 inches, roughly. So you can see these problems can be pretty crazy algebraically, but calculus-wise, it shouldn't be terrible. But I'm picking on the harder problem here. All right, so that does it for this video. We'll go ahead and in the next video, we'll cover volumes.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.